Lateral stability involves the study of moments about the longitudinal axis. If the aircraft is displaced away from wings level, the inclination of the lift vector will generate a side force, and the aircraft will start to move sideways through the air. This is known as side slip. From our study of directional stability, it is obvious that a side slip will generate a yawing moment. If we freeze the animation during the side slip, we can see that a side slip angle exists, and the resultant fin force will generate a yawing moment towards the direction from which the airflow is coming, and the aircraft will weathercock into the wind. We are seeing a sample of the interaction between lateral stability and directional stability, which will be fully explained at the end of this lesson. For the study of lateral stability, we will concentrate on the rolling moments generated by a side slip. The type of lateral stability is determined by the direction of the rolling moment generated by the side slip. If the side slip generates an unfavourable rolling moment, the aircraft will roll further away from wings level. This is unstable due to side slip. If the side slip generates no rolling moments, the aircraft will neither roll further away from nor back towards wings level. This is neutral. If the side slip generates a favourable rolling moment, the aircraft will roll back towards wings level. This is stable due to side slip. The degree of lateral stability an aircraft has is the net result of the contribution of its component parts. First, we will look at the contribution of the wing. As the aircraft side slips, the relative airflow is no longer parallel to the longitudinal axis, and the forward speed vector and the side slip vector give a resultant relative airflow from the side. It will be easier to see what is happening if a two-dimensional view is used. As the aircraft side slips, the relative airflow is from the side, which we can replace with a view of an airflow stream. We can see that the airflow path is partly over the top and partly beneath the fuselage. This airflow is around the fuselage where the wing is attached. First, we'll look at a wing mounted on the bottom of the fuselage. The wing into wind has a decreased effective angle of attack and less lift, whereas the wing out of the wind has an increased angle of attack and more lift. The difference in lift on each half of the wing will generate a rolling moment that rolls the aircraft further away from wings level. The aircraft has negative lateral static stability. The designers can reduce the unstable contribution of a low-mounted wing by fitting the wing on the fuselage at an angle. This is called dihedral, the upward inclination of the wing from the horizontal. Let's see how dihedral reduces the unstable contribution of a low-mounted wing. It is clear that dihedral removes the wing from the influence of the airflow around the bottom of the wing fuselage junction, and the airflow over the top gives more lift on the wing into wind and less lift on the wing out of the wind, which generates a rolling moment back towards wings level. Dihedral gives an aircraft with a low-mounted wing positive lateral static stability. We will now take a look at the high-mounted wing. The airflow over the top of the fuselage wing junction gives more lift on the wing into wind and less lift on the wing out of wind, which generates a rolling moment back towards wings level. An aircraft with a high-mounted wing has positive lateral static stability merely because of the wing position on the fuselage. Because a high-mounted wing gives the same positive contribution to lateral stability as does dihedral, a high-mounted wing is known as a dihedral effect. A designer may decide on a high wing configuration because a low fuselage position with the aircraft on the ground is desirable for ease of loading. Potentially, the dihedral effect of the high wing may give too much lateral stability. If so, the designer can reduce the stable contribution of a high wing by fitting the wing at a downwards angle. This is called anhedral, the downward inclination of the wing from the horizontal. Most jet transport aircraft have a swept wing to increase the efficiency of high-speed flight. In a right side slip, the wing into the wind has less effective sweep angle, and the wing out of the wind has more effective sweep angle. This gives more lift on the right wing and less lift on the left wing, which generates a stabilizing left rolling moment. The swept wing provides a stable contribution to lateral stability, so is also classified as a dihedral effect. If an aircraft has a high-mounted wing that is also swept, it will have two dihedral effects and may have too much lateral stability. If this is the case, the wing will require anhedral to ensure the proper amount of lateral stability. The fin has already been identified as the aerofoil that provides directional stability. But in the side slip, the aerodynamic force on the fin acts above the CG, which generates a small stabilizing moment. The fin, therefore, is also a dihedral effect, but a small one. The contribution of a ventral fin is very small indeed. As you can see, the aerodynamic force is in the same direction, but is acting below the CG, and is destabilizing. For all practical purposes, any contribution of the ventral fin to lateral stability is insignificant. The illustration shows the low pressure area on the top of the wing. Each half of the wing generates a share of the lift, and each component of lift will act at a certain distance from the CG. Any change in lift in a side slip will act through a given arm length to generate a rolling moment. When the flaps are down, the inboard portion of the wing generates a larger percentage of the lift, and each component of lift will be located further inboard. With the flaps down, any change in lift in a side slip will act through a shorter arm and generate a smaller rolling moment. Hence, with flaps down, lateral stability is reduced. As has become increasingly obvious, in a side slip, the lateral and directional response of an aircraft will be coupled. Side slip will simultaneously produce a rolling and a yawing moment. The type of lateral dynamic stability an aircraft will exhibit is determined by which type of static stability is dominant, directional or lateral. If directional static stability is dominant, the aircraft will suffer from spiral instability. If lateral static stability is dominant, the aircraft will suffer from Dutch roll, a combination of rolling and yawing. Because jet transport aircraft have a swept wing, they have a tendency to Dutch roll, and are fitted with a device called a yaw damper to prevent it.